Phew. I was entering all the grades. So you should have everything back except for fat characterization, which you submitted, the last lab report, and the project you're submitting today. So I'll see what I can do, get done before the final, so you know where you stand. But I will upload whatever grades I have by end of this week on Moodle, so you can have an idea of your standing before the final. Just a quick average of the quiz. Okay, let's continue where we left off with immunoassays. A little bit of a recap before finishing up the remaining slides. So what's the main principle of immunoassays? What are they based off of? One sentence. Two things. One word. Antibodies. She gave me one word. The second one is reaction with antigen. So it's based on antibodies reacting with an antigen. And the antigen can be any class of molecule, from protein to a mycotoxin, for example, to an antibiotic, so or a pesticide. So any compound that will have a specific interaction with an antibody. The antibody are produced by injecting the antigen in an animal host, collecting the blood, isolating the antibodies to use them in assays. What are some applications? Stephanie? Like allergens. When Myson sits down, he can take the participation. Right? You're already doing. He's multitasking. So, allergens. Another. Yes, Makia. Aflatoxin. So we said allergen, aflatoxin, mycotoxin is an aflatoxin, a mycotoxin. So authentication of meat. Pesticides, you can do immunoassays. Antibiotics. What is an epitope? Yes, it's a location on the antigen where the antibody binds. What is the difference between polyclonal and monoclonal antibodies? Yes, Lucy?
In polyclonal, there are like multiple spots on the antigen where it can bind, whereas monoclonal, there's only like one specific spot.
Yes. So monoclonal, you have a solution of antibodies, let's say, but all of them have a specificity to one epitope on the antigen. So they're all alike. Their binding site is all alike. Polyclonal, you have a mixture of antibodies, and they will have, each antibody is originating from a different B cell, so they will recognize a different epitope on your antigen. So they're not alike. They have different binding sites. So what are the main, how are they produced? Do you remember how we can produce monoclonal? By using cancerous cells that will multiply very fast and linking the B cells to the cancerous cell, one type of B cell, it will produce one type of antibody. Polyclonal, you just inject the antigen in the host, collect the blood. The host has subsequently multiple B cells types, so they will produce polyclonal antibodies. So now, what are the steps in sandwich ELISA? Sam?
Bind, wash, label, and read.
How simple is that? Bind, wash, label, and read. But let's go a little bit more specific. So you bind the antibodies, to a plate via hydrophobic interaction, put the sample. Of course, there's washing step. So you wash off any excess antibodies that did not bind. You have a blocking agent. This is very important. You have a blocking agent, a protein usually that is not present in your sample. Bovine serum albumin is most commonly used, or gelatin can be used. You bind the surfaces that has nothing on it, and then you add your sample. If you have the antigen will bind to the antibody. And then you wash off anything else that did not bind. Then you put another solution with antibodies. These will be your indicator antibodies. So they will be labeled with an enzyme. So the indicator antibody will bind, and thence you will have a sandwich of your antigen. And then you wash, then you put a substrate, the enzyme linked to the antibody will react with the substrate. You get a product, you measure absorption. What's the difference between direct and indirect ELISA? Stephanie?
Indirect might be an antibody to an antibody.
Yes, so in the indirect, that was the last thing we talked about last time. You would, let's see. So here, you would have your antibody that captures the antigen, and antibody that will capture it from another epitope, sandwich it. This antibody right here, the other one, will be an antibody to this antibody. So let's say this is a human antibody. You inject a human antibody in a rabbit or a goat, it will give you an antibody for it. This you can purchase already labeled with an enzyme. So you reduce a step in the lab, step in the analysis to make it easier. You purchase an already labeled one with an enzyme, horseradish peroxidase. So that's an indirect. So indirect because this one is not labeled, the blue one, the other one is labeled. And in sandwich ELISA, whether it's direct or indirect, the more antigen you have, the more absorption you're going to get, the higher absorption reading, because you have more binding of an antibody to the antigen, and then you will have more binding of the antibody to the antibody. So then when you put a substrate, you'll have more enzyme to react. If you don't have antigen, or if you have low concentration of antigen, you have less of this reaction occurring. So in sandwich ELISA, direct and indirect. Do you have a question? Okay. So direct or indirect, higher absorption, higher antigen. All right, so moving on to competitive ELISA. As the name implies, there will be competition going on between the antigen in your sample and a labeled antigen in the reagent that you will add. So the reason we use comparative ELISA is because when you're looking for detection of molecules that are small in size. So small, that means less than 5,000 Dalton, so grams per mole. So when you have less than 5,000 grams per mole, you can only have one epitope on that molecule. That means one region that the antibody can bind. If you only have one region, you can't sandwich that. You cannot have another antibody reacting. There's only one epitope. So in this case, you need something else. You need to do something different. And in order to generate antibodies for this antigen, you usually use what is known as hapten. Hapten is you bind that molecule, you bind it to a protein. You don't care for that protein. You can get bovine serum albumin or gelatin or any protein that you don't care for. So albumin protein, you bind it. You call that as a carrier protein. So that would be carrying the antigen, any molecule that is small. When it's bound to your antigen, it becomes a hapten. This hapten is what you inject in a host, and you get antibodies specific to your antigen. But at the same time, the body creates antibody that recognizes the carrier as well. Okay, so keep that in mind for the next step. So you get antibodies specific for the molecules as well as you get antibodies for the carrier. So what happens here, I will show you, not this picture, I'll show you on the next diagram what you can do. You can have a bound antibody form and a bound hapten form of ELISA. So what happens in the bound antibody form is you have your hydrophobic surface and then you bind your antibodies. And then what you do is you have your hapten that is labeled. The hapten, again, remember, carrier plus antigen, labeled with an enzyme. So in order to label an antigen that is small, that's the role of the carrier. The carrier allows for space to label, because this is a very small molecule. So you label the carrier with the enzyme. And then, so you introduced your sample and the hapten that is labeled, you introduce it to the, after you bind the antibodies and block, you introduce these together. This is your antigen from your sample, and this is the antigen that was bound to a hapten that is labeled. So bound to a carrier, meaning this is the hapten, enzyme labeled hapten carrier protein conjugate. And this is coming from your sample. So what's happening now is the antigen from your sample and the antigen that is bound to your hapten, they're competing. Hence, there's the competition. So the labeled hapten and the antigen are both competing for binding sites on the antibodies. Okay. So what happens now? The more antigen you have in the sample, the less labeled hapten is going to bind. So higher absorption means more antigen or less antigen in this case. Higher absorption, that means you have enzyme converting substrate to product. Higher absorption doesn't mean more antigen or less antigen in your sample. Less, because you have competition. So the more absorption you have, that means all of these labeled one has bound, and the unlabeled, there are not many of them. So the spaces are mostly taken by the bound hapten. Okay? So lower absorption in this case means higher antigen. Higher absorption means lower antigen. So if you have a lot of these antigens in your sample, they will compete and bind, then you'll have less enzyme bound, then less absorption. So that's the bound antibody. You can have bound hapten. That means you can have the protein hapten, the carrier, bind, and then you, instead of having a labeled hapten, you have a labeled antibody. And then you introduce the labeled antibodies and the sample. So if you have antigen, the antigen will bind to the labeled antibody and get washed off, and less antibody will bind to the hapten. Okay? So the same thing, they're competing. But the antibody is binding to the antigen in the sample, got washed off. You don't get absorption. You don't get the enzyme to function. And if you don't have antigens in the sample, more of these labeled antibodies will bind to the bound hapten. And then you'll get higher absorption. That means you have less antigen in the sample. Is this clear? Anyone would like me to repeat? You all got this. Okay. One note here is very important. When you are using an assay, you want to make sure that your carrier protein is different than the carrier protein you've used to produce the antibodies in the host. Okay? Because if this is the same albumin, for example, the antibody will bind to it instead of binding to the antigen. Okay, there will be non-specific binding. So the antibody will have more locations to bind on the carrier protein. So you want the carrier protein that you don't have antibody for. Remember when I told you inject the hapten in the animal, and the animal will produce antibodies not only for the antigen but also for the protein that got injected. So therefore in your assay you want to make sure you have a different carrier protein. So you don't want any non-specific binding that you don't want to happen. You only want your antigen to bind to the antibody. You don't want the antibody to bind to anything else. Okay, this is an example of aflatoxin. So this is showing you how the competitive ELISA works. So when you have no toxin, all of your labeled antigens are going, labeled hapten, are going to bind, and you have the highest absorption. When you have a lot of aflatoxin in there, some of the aflatoxins will bind to the antibodies, and very minimal amount of the bound hapten will find a location, so you'll have low absorption. Another form of immunoassay is actually immunoaffinity chromatography, where it's used for purification. You can use it to concentrate a certain antigen, or you can use it to isolate antibodies from a mixture, or isolate a specific antibody from a mixture, so you can produce monoclonal antibodies for higher specificity in the assay. Here's your lateral flow strip, which is a quick test based on sandwich ELISA. So a very good example, like was brought up last time, is the pregnancy test. And the yellow color is coincidental in this case. Anyway, so what you have here is you have the strip, you have different locations on the strip. So it's called lateral flow because your liquid is going to move up by lateral flow. So you immerse the strip, and the first portion of the strip here, this blue place here, you have antibodies that are specific and labeled with a color. And then they're going to be, if you have the antigen, say you have the protein that is in the urine that is specific for pregnancy, this will bind. And then by lateral flow, the antibody and the bound antigen are going to flow up to another location where you have another set of antibodies specific for that protein. So you will sandwich the antigen and fix it. Here you will see a color. So if we look at the actual test strip here, so that's the sample pad. You inserted, your liquid is going to move up. That's the test line, and that's the control line. The test line, you have another antibody for the antigen, so it will capture it and fix it as a sandwich here, and you see a color. You always have a control line to see if the assay is working. So if you don't have a protein in your sample that you're looking for, your antibody is going to continue to migrate up by lateral flow, and there will be here an antibody to the antibody. So this antibody to the antibody is going to capture the antibody that is colored, and then you will see a colored line. So whether your test is negative or positive, you always see the control line. If you don't see it, that means something is wrong with your strip. Throw it away, go buy a new one. And then if you see this line here, that means you have the protein, it got captured by the second antibody, and you see a color formed. So this can be done as a field test for GMO, as an application for genetically modified organism. So if you are in a field and you don't have sophisticated equipment, you can run this quick test to determine presence of GMO. Western blot is another immunoassay that is mostly qualitative, and you can do screening of multiple samples at the same time. So what you do, it starts off with running a gel. You run, in this case, a 2D gel. So you will have a mixture of the proteins, and you can run 2D, you can run one-dimensional as well. But oftentimes you run 2D gel, you will get spots of the different proteins. You transfer them to a membrane, a very hydrophobic membrane, so that you'll capture the proteins. You transfer them usually, I forgot to bring the Western blot. I usually bring the Western blot equipment with me, but anyway, you transfer them using electrophoresis kind of voltage into the membrane. So they go from your gel to the membrane, and from there you block with BSA, bovine serum albumin. Same with ELISA, you have to block to ensure you don't get non-specific binding. So you block all the areas that don't have protein on them with the bovine serum albumin. You wash off, and then you add the primary antibody, the antibody that will recognize an antigen on your membrane. So you incubate with that, then you wash, and then you put the secondary antibody that is labeled with an enzyme. So this antibody will react with the detection antibody or the capture antibody or the primary antibody. All the same thing, primary antibody, capture antibody. So if you have the antigen, you'll have this bound to it. If this is bound to it, then this antibody will bind to this antibody. And then you add your substrate, and you produce a product that is colored, and you can see it on your membrane after a series of incubation. So this is just an example application where you have different types of meat proteins loaded, and then to identify, let's say, pork protein, this was transferred onto the membrane and incubated with an antibody specific for pork, and nothing else bound, just that single point that you see, indicative of the presence of a specific protein in pork. Okay, so that's that for immunoassays. So 2 more chapters left that somehow I will try to finish between whatever is left today and Wednesday. So this is now chapter 33. It used to be chapter 18. It's now chapter 33 in your new book. It's analysis of food contaminants, residues, and chemical constituents of concern. It's a long chapter, has a lot of information. A flower from every garden, I call this chapter. It took me a year to write this chapter. Anyway, I will summarize it in 20 minutes. No, it won't finish in 20 minutes. Okay, so there is a lot of places where a sample can be contaminated, either contaminated or it will get contaminated along the way. Starting from farms, during transport, during processing, storage, in supermarkets until it reaches to the consumers. Can you think of any contaminants or residues in any area or place in this circle of life? Circle of food. Any contaminants or residues that are concerning that might form in the food product or get into the food product? Julian?
Like insects?
Insects. Okay. So insects you can get insects in the farm, you can get insects during transport and storage. So this is actually the topic of the next chapter, which is extraneous matter.
Antibiotics?
Where do we get the antibiotics? It starts with here. From the animals on the farm, they get antibiotics. Yes, Danny? Pesticides starts with produce on the farm. Megan? Aflatoxins, mycotoxins, so during storage of grains, let's say, or nuts, you get fungus or molds, then you can generate mycotoxins.
I would say allergens.
Allergens, yes, so it's actually, this is something that we don't introduce, it's present in a product, of milk, or soy, or peanut, it's naturally present proteins, they get to be there. What else? Bailey?
Do you have like chemicals from like cleaning processes?
Chemicals, yes. So chemical contaminants from cleaning or chemical contaminants that you get through adulteration, intentional adulteration, such as? Melamine is one, it happened. So such as melamine. Another, you add sulfites. So sulfites, people have sensitivity to it. You have to state on the label. You added, why do we add sulfites sometimes? Yeah? Yeah, for browning. So you added to dried fruits and vegetables to prevent browning because it's a reducing agent. You add it as an antimicrobial agent. It can be added present naturally in wine or added to stop the fermentation process. So let's see what else. Bisphenol A, it leaks from a packaging material into the product, into the water, for example, from the water bottle into the product. So there are chemicals, there are, of course, you have the microbes. We're not dealing with microbes, but we have the aflatoxins, we have pesticides, antibiotics, intentional adulteration, and we have the chemicals that form during processing, such as furans, acrylamide, heterocyclic amines, nitrosamines. All of these are chemicals that form during processing that have bad health effects. Okay, so a lot of recalls. This is an old chapter. The new book it doesn't have a figure, the new book chapter, it has new numbers. But you do get a lot of recalls, a lot of calls for, or reports for contaminants and residues of concerns. So a big portion of it is chemical. We talked about antibiotics, sulfites, heavy metal, presence. Mycotoxin is another big portion of the reports. Microbiological for bacterial or mold. Others, the fraud such as melamine, biological hazards, labeling, problem with the labeling, and then chemical hazards, quality, hygiene, defective packaging, etc. So the categories, we have pesticides, drug residues, and mycotoxins. You have governmental tolerance level. So you have levels that are acceptable. Below certain level, it's acceptable. Some mycotoxins, for example, tolerance level is 0. So So there are regulations about the type of pesticides that can be used and the amount of pesticide that can still be present. Same with the drug residues. So there are regulations about that. Allergen, there are regulations in terms of labeling. A lot of recalls happened because of allergens not properly labeled on the package. And then chemical additives, mostly those that are either generated during processing or added as an adulteration or actually added as a food additive during processing, like sulfite or nitrite for meat production. So this is a summary table that is really good for you to know, because it summarizes different categories of important residues, main quantitative methods, and qualitative methods. So we'll go over all of these, but this is a good summary table. So for that one question that we went over in the review session, when asking the type of contaminant in a product, what would be a method of detection, then that would be a good table to go to. So when preparing a sample to measure contaminants of concern, since most of these are present either randomly or in a very, very small concentration, so it's very important that the sample is homogenized. And the sample is representative of the population. If you remember when we were talking about sample preparation and sampling at the beginning of the semester, we said it's very important to have large number of samples pulled when you're looking at residues that are not randomly distributed or present in a small concentration. So we gave the example of mycotoxins, and here it is. So we really have to have a representative sample of the population and quite a bit of numbers pulled out to make sure that we don't miss anything. To make sure that, since especially mycotoxins, some of them is zero limit of tolerance. So this is a very crucial step. So sample homogenization and sample pulling out sample as well as sample preparation are more important for chemicals of concern than the actual method. So errors in homogenization or pulling out samples or sample preparation will cost us more than errors in the actual sample method analysis. So more weight is put on the preparation and getting a sample. So basically this is kind of the flow of steps. Start with collecting and storing the sample and then preparation of the sample. In most cases there's an extraction step, and usually it's a solvent extraction step. And then fractionation and cleaning. Concentration is very important because pesticides might be present in a very small amount, or mycotoxins, or in residues, that's hence the name residues, present in very small concentration. So in order to increase sensitivity, there is a concentration step. Derivatization is there just in case we are aiming to run by GC. Oftentimes, many of these constituents are analyzed by GC, so there is a derivatization step. Then analysis, in most cases, if it's quantitative, it will be chromatographic analysis, either HPLC or GC, and linked with MS. You'll see that many of the analyses is HPLC-MS or GC-MS, because you're looking for accurate identification and quantification of these residues. And then after you identify and quantify, there is the reporting. So how do we choose the method, whether a method of extraction or a method of analysis? Like with everything, it depends on the food matrix. What we know about the analytes, is it hydrophobic? Is it charged? How are we going to separate it from other components? Is it volatile? Is it non-volatile? Polar, non-polar? So we need to understand the properties so that we determine what methods to use. And feasibility, sometimes two different methods would work, but what's more feasible, cost effective, less complicated, give me the answer that I need. And whether I want to go for multi-residue or single residue. What I mean by multi-residue is, let's say I'm looking for pesticides. And I know that this farm is using 5 different pesticides. So I need a method that will allow me to detect all of them and quantify all of them. We call this multi-residue analysis. Single residue, and this is often used to determine levels of tolerance levels by the government. So they would actually do an extraction that is very, very specific to one component. And they would measure that one component. So single residue has a specific purpose, whereas multi-residue is more efficient and for quantification purposes and identification in a number of samples, it's better to go with multi-residue. So this is again the steps. Separation of edible and non-edible fraction, homogenization, whatever is the sample, chopping, grinding, blending. And then often, like I said, it's extraction by a solvent and filtration. So cleanup of the sample, you can do that by size exclusion or adsorptive or affinity chromatography. There are other quicker ways. We talked about this in the GC chapter, the solid phase extraction and solid phase microextraction. But this specifically stands for quick, easy, cheap, effective, rugged, and safe. Wow. Those are rugged. R-U-G-G-E-D. Like very, what do you call it? Like a rugged. Ah, rugged, robust. What did I say? Rugged? Rugged? Forget me. R-U-G-G-E-D. Okay. Yeah, I know. Put you on the rug and smash it. Yeah, this is how we rug it. Yeah, no. Okay, so usually then that's based on having an absorptive surface that would just take out other components that you don't care for and clean up your sample. Or the other way around, selective to your product that would selectively bind to the surface and you can isolate them and concentrate them that way. Accelerated solvent extraction, another way of cleanup. Talked about that in fat extraction. The analysis, like I said, is more often than not, it's GC, HPLC. TLC is only like a qualitative method for screening. Oftentimes, you just want to screen if you have pesticides. If you have them, then you go and quantify them. So mostly the TLC is used for screening. And derivatization there is when you're doing GC that you're working with compounds that are not volatile and not thermally stable. Most of the time you do MS for these kind of analyses, and immunoassays you can do semi-quantitation. Okay. I deleted one slide from what you have just because it was a repetition to the one that I showed. So forget about that. So pesticides. So there are so many pesticides out there, and in order for any farm to use a pesticide, it has to be registered. So you have over 1,300 different registered pesticides that can be used. So quite a bit of those. Like I said, most of the time in order to quantify them, we approach it via multi-residue analytical methods using GC, HPLC. Single residue, this is for setting the limits and identifying it and developing methods. So it's not often used for regulatory purposes. The single residue method, which is directed to just isolating that one pesticide, for example. Semi-quantitative and qualitative, so again, it's screening methods to determine presence or not. So it will be thin layer chromatography, and enzyme inhibition. So quantitation with GC is most common for those pesticides that are nonpolar. In the past, almost all pesticides used were nonpolar. Most recently, they've started to come up with new pesticides, and they tend to be polar, so HPLC became another method for pesticides. So choice of columns vary depending on what analytes you have. Same with detectors, what components the pesticides would have. You would have different detectors that would work best for the components. This is showing you a multi-residue analysis of multiple pesticides that is present, 5 organophosphate pesticides. Because you have organophosphate, so they use the flame photometer, which can detect phosphorus. This is HPLC, and again, it's a multi-residue. These are for analytes that are polar and non-volatile or thermally stable. Again, choice of columns, the same thing with GC, depends on the analyte, and you can have a range of detector, UV, fluorescence, or in most cases, it's MS, because you want to identify as well as quantitate. So this is just a reminder for your MS, and to remember that MS is important to review for the final. So with the MS, you get a spectra, and you would be able to compare it to a standard or a library to confirm the identity. And if you do MS-MS, you get even more identification. That means MS in tandem. You would take a fraction and fragment it again to get more identification and get rid of the noise. This is an example where you have a lot of noise with the first MS. If you take a second MS, you will have much cleaner spectra that you can compare to a standard and confirm identification. Pesticides can be determined using ELISA as well as thin layer chromatography. So how they do it with thin layer chromatography is you run your samples on the TLC plate, then you spray the sample, you spray the plate with enzyme solution. The enzyme is a specific enzyme that is inhibited by pesticides. So they inhibit this pesticide, and that's how the insect will die, or the pest would die. So they spray the whole plate with this enzyme, and then they spray it with a substrate specific for that enzyme. The substrate will produce color. If you have a pesticide in there, it inhibits that enzyme. So you don't see colors, you just see zones, clear zones. That means here the enzyme is being inhibited because there is a pesticide there. So that indicates the presence of pesticide. So mycotoxins, so there are metabolites of fungus. There can be many different classes of mycotoxins, and the major toxins are aflatoxins and ochratoxins. Harmful to humans, poultry, livestock, and they're potent carcinogens. And then they are present in very low concentration if they are, and they have very low tolerance levels. Some of these potent mycotoxins that are carcinogen and genotoxins, they should be present or not present at all. 0 is the tolerance limit. So methods of analysis ranges from thin layer chromatography, reverse phase, HPLC, UV or fluorescence, add to that MS detection. Immunoaffinity, ELISA, that's the competitive form of ELISA. I have 1 minute. Let me finish that. Drug residues, they are given to the animal in 2 cases. either therapeutic levels to treat an infection or subtherapeutic to prevent an infection and to increase weight gain with less feed, kind of cheating the animal. But in this case, if there's a potential problem if the antibiotics remain in the milk, hypersensitivity of people. Some people are allergic to mycotoxins. And also it interferes with the production of cheese and yogurt. So if you have antibiotics, the bacteria or the culture will not grow. And also the animal will produce resistance, the bacteria will produce resistance to these antibiotics. And then if we're producing the meat, there shouldn't be antibiotics in the cow or any animal before slaughter for a certain period of time, as well as milk production. They should stop antibiotics before milk production. Okay, I'll stop here and continue next time.
Everyone had 3 pieces.